Mr. Clown here for Clown Maths. I'm going to do some advanced higher maths today. I'm going to do integration. Now, all these exams are taken from my excellent website, maths.scot. So make sure you look there for some extra revision. But I'm going to go through pretty much a whole topic, question by question, hopefully one or two for each of the different types that you might see in your exam. Hopefully you find this useful. Okay, example 1 says integrate 3x squared minus 1 over 2x cubed minus 2x cubed minus 2x plus 1. It looks almost impossible. However, this is, notice how they're kind of like 1 power away. So if I differentiate one, I'm going to get a squared. So I'm going to try that. So I'm going to kind of say, like, let u equal 2x cubed minus 2x plus 1 and see what happens. So if I do the u by the x, I get 3 2s is 6x squared minus 2. Well, that's sort of 3x squared minus 1. It's just a multiple. So I could say I've got 6x squared minus 2 dx equals du, and therefore if I'm wanting 3x squared minus 1 dx, then that's a half du. So now it's kind of an integration by substitution. Now there's a rule you could remember which turns this into a log, but I prefer to just not remember loads of rules, so I'm going to do it like this all the time. So that means I now need to integrate. So my integral becomes very simply a half du, and u was that, so u on the bottom as well. So u is now on the bottom. So I've got du over 2u. That's as simple as that, because you've got your u just turning into here. And then we've got a half, so 2 on the bottom as well, and then du on the top. So we can integrate that quite easily. Start of exam paper, 1 over u is log u. So that's a half of log u plus c. But u, remember, was our original thing of 2x cubed minus 2x plus 1. So that's a half log 2x cubed minus 2x add 1 plus c. And we're done there.
Clever Maths is sponsored by Lecky, the educational publisher for Scotland. They offer viewers of this channel a massive 30% discount. Just use the discount code CleverMaths at leckyscotland.co.uk. Their practice question books go all the way from level 3 to advanced higher and include National 3, 4 and 5 apps as well, so you can get any book you need for your studies. These are an excellent resource with questions on every topic and contain work solutions so you can see how the marks are awarded. As you go through the book, the questions get increasingly difficult, so by the time you finish your book, you'll be ready for your exams. Usually £9.99, just use the discount code CleverMaths to get 30% off that. Link down below.
Now remember, I've got a members only channel for £4.99. I'll be doing regular live streams, especially for advanced higher as the year progresses, so make sure you get on that. Example 2, integrate 6 dx over the square root of 4 minus 9x squared. So this is one of the ones where the start of the exam paper does help a lot with these. If you ever notice there's something squared on the bottom, especially like a square root, you're looking at the start of the exam paper because it's probably an inverse trig function. In this case, it is a standard integral. The standard integral at the start of the exam paper is the square root of dx over this a squared minus x squared gives you the inverse sine of x over a plus c. So I just need to identify that for my integral. So my integral is the integral of 6 dx over the square root of 4 minus 9x squared. So that's going to be the integral of 6 over the square root of 2 squared essentially minus 3x all squared dx. So that means that when I integrate it, I'm going to have my 6. I'm going to have my inverse sine. I've got x squared, which is 3x squared, so that's 3x over 2. But since it's now 3x instead of x, I need to divide by 3 as well. A bit like the chain rule, I suppose, plus c. So that gives me 2 inverse sine 3x over 2 plus c. And we're done there. Example 3, SQA Advanced Higher Maths 2018, question 2. Find partial fractions to integrate this. So I need to do partial fractions first. So I've got 3x minus 7 over x squared minus 2x minus 15 equals, well, 3x minus 7 over x and x, 3 and 5. And it's going to be minus 5 plus 3 to make minus 2. And that equals a over x plus 3 then, plus b over x minus 5. So that implies that ax minus 5 plus bx plus 3 equals 3x minus 7. So now we can just try and work this out by saying that let's x equal 5, and that will eliminate 5 minus 5 is nothing. 5 plus 3 is 8, gives me 8b equals 15 minus 7 is 8, so b is 1. Similarly, when x equals negative 3, we get negative 3 and negative 5 is negative 8. A 3 times minus 3 is minus 9. Minus 7 is minus 16. So a is 2. So now our integral becomes, we've got a over x plus 3. So 2 over x plus 3. Plus b, which is 1, over x minus 5. And now it's easy, because the whole point of doing this is that that gives you a number over a linear function, which just integrates to a log. Start of the exam paper tells you that 1 over x goes to log x. So 2 over x plus 3 goes to 2 over log x plus 3, plus 1 log x minus 5 plus c. Now just watch out for these linear functions here. If there's a negative x in there or something, you need to be very careful. You need to maybe differentiate it and divide by it, so sometimes you get a negative coming out. You could leave it like that, or if you want to play with it, you could turn it into one log. Let's do it for fun. So that's log x plus 3 all squared plus log x minus 5 plus c. That's a 5. So you could change that to log x plus 3 squared times x minus 5, or x minus 5 times x plus 3 squared. Probably looks nicer, but then plus c on the end, and we're done there. Example 4, SQA Advanced Higher Specimen Paper, question 11. Find the exact value of the integral between 1 and 2 of this. So again, we're using partial fractions. So let's just do that first. X plus 4 over x plus 1 squared, 2x minus 1 equals a over x plus 1 plus b over x plus 1, but this time squared, plus c over 2x minus 1. So now we can then say that we've got a, well, a's been times by, it's got an x plus 1 still to get, and a 2x minus 1, plus b, well, that's got an x plus 1 all squared already, so that just needs a 2x minus 1, plus c needs an x plus 1 squared, and that all equals x plus 4. So let's just eliminate by picking our x's carefully. If we pick x equal to minus 1, then that will eliminate a and it'll eliminate c. So that'll give me 2 times minus 1 is minus 2, minus 1 is minus 3b, equals minus 1 plus 4 is 3, which means that b is minus 1. We'll now pick x to be something else. Well, I think we want to get rid of the 2x minus 1 here. So if we let that equal to 0, x would be a half. And that means that a and b are gone, and we've got 1 plus a half squared. Well, that's 3 halves. I'll write this one out actually. 3 halves squared equals a half plus 4, or 4 and a half. We don't want 4 and a half, do we? I'll write a half plus 4, then you'll be able to see it. So that is 3 3s is 9 over 4c equals 4 is 8 plus 1 is 9 halves. So we could say that that implies that 9c times 2 is 18c equals 9 4s is 36. 36 divided by 18 is 2. So finally we get 2. And then we just pick any old number. So let's just pick x equal to 0. If we do that, if we go way back up, we get 1 times minus 1 is minus 1, so we get minus a. For the b part, we get minus b. And for the c part, we get 1. And on the right-hand side, that's going to equal 4, 0 plus 4. b is minus 1, c is 2, so we get minus a. Minus minus 1 is plus 1, plus 2 equals 4. That's minus a plus 3 equals 4. 4 minus 3 is 1, so a is minus 1. So now we can integrate. So we've got our partial fractions that we're integrating between 1 and 2 of minus 1 over x plus 1 and minus 1 again over x plus 1 squared, and c is 2 over 2x minus 1 dx. So we need to integrate these, so just integrate them separately. Just watch it for that middle one. It's not a log, it's just a squared. So we're just going to use a chain rule. So that becomes minus 1 log x plus 1. This term here is x plus 1 to the minus 2. So we add 1 to the power, which is minus 1. And then we divide by the new power, but we also divide by x plus 1 differentiated, which is 1. So divide by minus 1. And then plus 2 log 2x minus 1. So it's 2x minus 1. So again, we differentiate that to get 2 and divide by it. And that's all between 1 and 2. So that gives me minus log x plus 1. Minus divided by minus is plus. So plus 1 over x plus 1 plus 2 divided by 2 is 1 log 2x minus 1. Now the question did want the exact value. So we're going to be manipulating this. And that's between 1 and 2. You can bring your logs together now or later. It is up to you. I'll do it later. So let's just put my numbers in. So I've got minus log 2 plus 1 is 3, plus 1 over 2 plus 1 is 3, plus log of 2 2's is 4 minus 1 is, well, 3. So that's my first term. Take away minus log 1 plus 1 is 2, plus 1 over 1 plus 1 is 2, plus log of 2 1's is 2 minus 1 is 1. So a bit of manipulation here. Log 3 minus log 3 is nothing, so the first bracket's got a third. We just cancel each other out. Log of 1, you should remember, is also 0. So that becomes minus minus plus log 2 minus a half. So I need to do a third minus a half. So we've got log 2. 2 minus 3 is minus 1 sixth. Log 2 minus a sixth. And that's about as exact as I'm going to get. So I'm done there. Example 5, use the substitution u equals tan x to find this. So if I was using substitution, integration by substitution, I need to find the u by dx. So start of exam paper tells you that tan x differentiates to sec squared x. So that means that du is equal to sec squared x dx. Or in other words, dx is du over sec squared x. You might think that doesn't help us, but let's just keep going and see what we get. We'll substitute it in. So subbing in, we've got the integral of du over sec squared x times 1 over sine x cos x. Doesn't look like much now. We've still got sines and coses and x's, and we don't want x's in anything. But we'll simplify that and see what we get. Remember, sec is 1 over cos. So that first thing becomes cos squared x times 1 over sine x cos x. I'll just shove the du sitting on the end. Well, 1 of the coses cancel, so that gives me the integral of cos x over sine x du. The cos x over sine x is 1 over tan x. But it says u is tan x. Well done, there we go, we've got our u out. So here we go. That is the integral of 1 over u du. Start of exam paper tells you that's log u plus c. Make sure you put your bars around that, it's the exact value. So u is tan x, so that's the log of tan x plus c. And we're done there. Example 6, SQA Advanced Higher Maths 2018, question 8. Use the substitution use sine theta, or otherwise, to evaluate the integral between pi over 6 and pi over 2 of 2 sine 4 pi cos pi of 2 sine 4 theta plus cos. To evaluate the integral between pi over 6 and pi over 2, 2 sine 4 theta cos theta d theta. So we'll start with our substitution. Sine theta. That means the u by d theta is cos theta. That means the u is cos theta d theta. So we can sub in and see what we end up with. So we've got our integral. We'll fix the limits first, I think, actually, because we're going to change these limits out. So when you've got limits, fix them. So u is sine theta. So when theta is equal to pi over 6, u is sine pi over 6. Well, that's an exact value. Pi over 6, remember, is 30 degrees. So the 30 degrees gives you a half as an exact value. And when theta is pi over 2, then u is sine pi over 2. That's sine of 90 then. The sine of 90 is 1. So that's just 1. So the integral becomes the integral between a half and 1. I've changed the limits of 2 sine 4 theta, u to the power of 4 then. Cos theta d theta is the u. Well, that's handy. So that's nice, easy to do. So that gives me 2/5 u to the 5 between a half and 1. Subbing in then, we get 2/5 minus 2/5 again of a half to the power of 5. Non-calculator this, so that's 2/5 minus 2/5 times 1 over 2 2s is 4 times 2 is 8 times 2 is 16 times 2 is 32. We could take 2/5 out as a common factor here to make it easier, and that just gives me 1 minus 1 over 32, and then work out that. Or you could have just done 2/5 times 1 over 32, then took it away for 2/5. Your choice. But I'm going to do it this way because that just makes my brain easier. 1 minus 1 over 32 is 31 over 32. So I'm timesing them together. Well, I might as well simplify that now by 1 and 16. And that gives me 31 over 5/16. 5/10 is 50. 5/6 is 30. Makes 80. 31 over 80. And we're done there. Okay, example 7, we reach integration by parts. SQA Advanced Higher Maths 2023, paper 1, question 4 had use integration by parts to find x to the power of 4 log x dx. So this is a standard, like just one round one. There's ones that go around in circles, but this is quite an easy one. So integration by parts, we need u and v, and it's a bit like the product rule in reverse. It's like the product rule for integration, essentially. So we'll let one of them be u and one of them be v dash, because the integration by parts says the integral of uv dash equals uv minus the integral of vu dash. So if we want that, then we want really this new term that we end up under here to be as simple as possible, something we can actually integrate. Now, this is quite obvious here, but log x, do we know how to integrate log x anyway? We don't. So log x has to be our u. So we're going to say that u is log x, which means u dash is 1 over x. V is x to the 4 then, but it's v dash. So v dash is x to the 4. So integrate that to get v, which is a 5 x to the 5. So that means our integral becomes of x to the 4 log x dx becomes u times v, 1/5 x to the 5 log x, minus the integral of v again, which is a 5 x to the 5, times u dash, which is 1 over x dx. Well, that's handy because that'll be integratable. So that gives us 1/5 x to the 5 log x. There's also a plus c, but I'll just put that on at the end. Minus, I'll just take the 5th out to make it easier, x to the 4 dx. So that's 1/5 x to the 5 log x minus 1/5 times 1/5 x to the 5 plus c, 1/5 x to the 5 log x minus 1/25 x to the 5 plus c. And I think we'll be done there. SQA Advanced Higher Maths 2016 Specimen Question 5. Find the integral of x squared e to the 3x dx. Well, again, it's two functions smooshed together, times together. So it must be integration of parts. But e to the 3x will never disappear. So it's the x squared is the one that's going to go. But if you think about x squared, if you differentiate it once, you get 2x. If you differentiate it again, you get 2. So you're going to have to do integration of parts twice. Now, as soon as I get one where I have to do it more than once, I'm going to switch methods here and use something that's much more simple called the DI method. Okay, well, it's as simplified as that. Here's what you do. I'll show you this. Maybe you don't like it, and if you don't like it, then use standard integration of parts twice. But hopefully you see the power of this, of how quick this is. So we call one of them D, the one we're differentiating, and one of them I. So the one we're going to differentiate is x squared, I would say. And the one we're going to integrate is e to the 3x. We'll just write plus, minus, plus, and so on. And we'll just differentiate this to get 2x. Integrate this to get e to the 3x times a third. Differentiate this to get 2. Integrate this then to get 1/9 e to the 3x. And we keep going until we get 0 and 1 in the differentiation place. So that is going to be 1/27 e to the 3x. Now our integral of x squared e to the 3x dx is now easy. It literally is just that times that minus that times that plus that times that minus 0. So that's x squared e to the 3x minus 2x over 3, 2/3 then, e to the 3x plus 2 over 9 so that's just 1/3 x squared e to the 3x, that times that, minus that times that, so minus 2 over 9 x e to the 3x, plus that times that, plus 2 over 27 e to the 3x plus c. And would you believe, we're done there. Example 9, use integration by parts to obtain integral of e to the x cos x. So this is going to be quite circular, this one. So let's just say that the one we're going to integrate is the cos x. So u dash is e to the x and v is sine x. So that means on the first go round, let's say that that's called I, or integral. I is, remember, uv e to the x sine x minus the integral of vu dash, which is e to the x sine x. So now we can start doing integration by parts on this bit. So let that be my u and that be my v dash. So then my u dash would equal e to the x again, and my v would equal sine x integrates to minus cos x. So that means that my integral now becomes e to the x sine x minus u times v. So uv is minus cos x e to the x minus the integral of vu dash. So v times u dash is minus cos x e to the x dx. So that means we've got I equals e to the x sine x. Minus minus makes plus cos x e to the x. Minus minus makes plus, but then another minus, minus. This whole thing here is just I. Minus minus is plus, and that's I. So that's minus I. So moving the I over, we get 2I is e to the x sine x plus e to the x cos x. Or taking e to the x out as a common factor, sine x plus cos x. If 2I is that, then I is a half of that. So it's just 1/2 of e to the x sine x plus e to the x cos x. I've missed a c, of course, so I'll just keep putting the c back in. Plus c, because you can just half a c and still have a c. And we're done there. Example 10. SQA Advanced Higher Maths 2016, question 9. Obtain x to the 7 log x squared integral. So, integration by parts. So, I don't want, as uv dash, remember, I don't want u to be x7 because I don't understand how to integrate log of x squared, never mind log x. So, I'm going to then say that that one is my u and that one's my v dash. So therefore, v is equal to 1/8 x to the 8, and u dash is 2 log x still, then times my log x differentiated, which is 1 over x. So now our integral, let's call it I becomes uv, which is log of x squared 1/8 x to the 8, minus the integral of vu dash 1/8 x to the 8 times 2 log x over x dx. So let's see what that gives us. That's 1/8 x to the 8 log of x squared minus 1/8, well, 1/8 times 2 is 2/8, so it's a quarter. So I'll just take that quarter out. And now we've got the integral of x to the 7 log x. So now examining this one, we have got x to the 7 log x, so uv dash again. So let's make that v dash and that u. Then v is equal to 1/8 x to the 8, and u dash is just 1 over x. So our integral becomes what we've already got, minus a quarter of uv again. So log x, 1/8 x to the 8, 1/8 x to the 8 log x, minus the integral of vu dash, which is 1/8 x to the 8, but vu dash is over x. So that's actually now going to be doable. So we then get 1/8 x to the 8 log of x squared minus a quarter of 1/8 x to the 8 log x, and minus an 1/8 of, well, x to the 8 over 8 is x to the 7, so that integrates to 1/8 x to the 8, and we'll have some sort of c on the end. So finally, we get that down to 1/8 x to the 8 log of x squared minus 132 x to the 8 log of x. 8 eighths is 64. 64 times 4 is 156. So plus 156, 256, x to the 8 plus c. And we're done there. 11. Use integration to prove that the volume of a sphere of radius r is 4/1 pi r cubed. Right, let's have a look at this. So imagine from higher maths that we've got a circle. We know the equation of a circle is x squared plus y squared equals r squared, assuming that the centre is 0, 0, of course, yeah? So now we can rearrange that to get y squared is r squared minus x squared. So that means that y is the square root of r squared minus x squared. It's on the origin, but if we just take the upper portion of it, then you'll have a picture that looks a bit like this. We're taking the upper portion, of course, because we want to be able to integrate it because it's a function, so it's the square root, the positive of it. If we then rotate that around this x-axis, you can imagine that that will then end up becoming a sphere. Now this lower limit will just be the minus r, and that will be r, because that's the centre there, so that's the radius. So all we're doing then is integrating. Our volume becomes the integral between minus r and r of pi y squared dx, because we're rotating around the x-axis. So we already know what y squared is. It's r squared minus x squared. So that's the integral between minus r and r of pi r squared minus x squared. Now x r squared, remember, is just a constant. So that becomes integral to minus r and r of pi r squared minus pi x squared dx. So that equals pi r squared is pi r squared x, because r squared and pi are just constants, minus pi 1/3 x cubed between minus r and r. So subbing in our r, for the first term we get pi r cubed minus 1/3 pi r cubed again. In the second term, we get pi r cubed again, but this will be minus because it's minus r for the x. And then minus r cubed is minus r cubed, but times a minus is a plus. So plus 1/3 pi r cubed. Tidying all that up, we've got pi r cubed minus pi r cubed is 2 pi r cubed. We've got minus 1/3 minus another third is minus 2/3 pi r cubed. 2 pi is 6 pi over 3 r cubed minus 2/3 pi r cubed. 6 minus 2 is 4, so that gives you 4/3 pi r cubed, which is exactly the volume of a sphere, and we're done there. SQA Advanced Maths 2017, question 16. On a suitable domain, a curve is defined by 4x squared plus 9y squared equals 36. A section in the first quadrant is shown, rotated 360 degrees about the y-axis. So if we're going about the y-axis, we want the integral of pi x squared dy. So we need the function, we need to know what x squared is. And our limits, we're going about the y-axis, so we need these two numbers. So we've got when it's 0, and then when this one is when x is 0. So when x is 0, we get 9y squared equals 36. So y squared equals 4, so y must be 2. The integral between 0 and 2 of pi x squared dy. So let's just work on that. So that's the integral between 0 and 2. I'll take my pi out because there's no need, it's a constant of x squared. So what is x squared? Well, 4x squared we already know must be 36 minus 9y squared. So x squared must be a quarter of that. So 36 over 4 is 9 minus 9 quarters y squared. So x squared is 9. So x squared is 9 minus 9 quarters y squared dy. So we can just integrate that. That's pi times 9y minus 9 over 4 y cubed divided by 3 between 0 and 2. So that's pi 9y minus 9 over 12 y cubed. So that's pi 9y, 9 12ths is 3 quarters, y cubed between 0 and 2. Subbing in now, we get 9 2s is 18, 2 2s is 4 times 2 is 8, 8 3s is 24 over 4, minus 0, and pi is getting times by all of that. That's pi 24 over 4 is 6, 18 minus 6 is 12, so we get 12 pi units cubed, and we're done there. Example 13, SQA Advanced Maths 2019, question 16. Use integration by parts to obtain the exact value of that, and then we've got a volume of revolution question. Now, with this integration by parts question, since one of these will differentiate to 0, namely this eventually, we can use the DI method, which is a lot quicker, and you'll see this. But if you don't like that, you can use integration by parts over and over, probably once or twice, probably twice, I think, to do this. But I'm going to show you the DI method again. I've got D and I. The one I'm differentiating is the one that's going to disappear, x squared minus 2x add 1, and the one I'm integrating is e to the 4x. So that gives me 2x minus 2, and that gives me a quarter e to the 4x. We're integrating, and that gives me 2, and that gives me a 16th e to the 4x. And then I've got 0, of course, and that gives me 1 over 64 e to the 4x. And remember, you've got your signs plus, minus, plus, minus. Now, what this means is our integral becomes that times that minus that times that plus that times that minus nothing. So our integration just becomes 1/4 x squared minus 2x plus 1 e to the 4x minus 2x minus 2 times a quarter again, a 16th, e to the 4x plus 2 over 64 e to the 4x, all between 0 and 1. Now we can tidy that up and then substitute our numbers in. So putting our numbers in, if we put 1 in here, we get 1 minus 2 plus 1, which is 0. So the first term gives us 0. Putting 1 into here, we get 2 ones is 2, minus 2 is 0. So we get minus nothing again. Putting 1 into here, we just get e to the 4 times 2 64ths, which is a 32nd. So plus 1 over 32 e to the 4. Now we need to take away when we put in 0. So for the first term, we've got 0, 0, 1. So 1/4 e to the 0, which is, well, 1. So that's just a quarter. And then we've got 0. So minus 2 times minus a 16th is positive an eighth e to the 0. So 1/8. And then the last term, e to the 0 is 1. 1 over 32. So we get that. Tidying that up then, we've got 1 over 32 e to the 4. We can make this all out of 32, so timesing that by 8, we would get 8. Timesing that by 4, we get 4. 8 and 4 is 12, and 1 is 13. So minus a 13 over 32, or if you want, you can take 1 over 32 out and have e to the 4 minus 13 in brackets, and there's your exact value, and we're done there. Part B says, I solve this form by rotating the curve of equation y equals 4 bracket x minus 1 e to the 2x between 0 and 1 through 2 pi radians. Find the exact value of this solid. Part B must follow on from part A, surely, so let's have a look. So remember, if we're making a volume of revolution and it's through the x-axis, then the volume is pi y squared dx, and it says we're going to do that between 0 and 1. Our y is 4x minus 1 e to the 2x. So I suppose the question becomes, what is that squared? So if we square that, y squared is 4x minus 1 e to the 2x all squared. Well, that's just a series of terms squared, so I can just split that up into 4 squared, x minus 1 squared, e to the 2x squared, well, that's just 4x. Or in other words, 16 x minus 1 squared e to the 4x. Now let's have a look to see what we integrated a minute ago. We integrated x squared minus 2x plus 1 e to the 4x. Well, let's expand that bracket and see what we've got then. 16 x squared minus 2x plus 1 e to the 4x. We've already integrated x squared minus 2x plus 1 e to the 4x between 0 and 1. So it should be pretty easy. So our integral, our volume, is the integral between 0 and 1 of 16 pi times x squared minus 2x plus 1 e to the 4x dx. But that's 16 pi is a constant, so, and it's times, so I can just take that out. So it's 16 pi times the integral of 0, 1 of x squared minus 2x plus 1 e to the 4x dx. But we already know the answer to that because we did it in part A. Our answer was 1/32 e to the 4 minus 13. So that's it. It's 16 pi times 1 over 32, and that's in brackets, I think, again, e to the 4 minus 13. And we'll just tidy that up slightly. So 16 times over 32 is a half, so that's pi over 2 e to the 4 minus 13 units cubed. inverse our volume, and we're done there. It's been Claire Maths today. We did some advanced higher maths on integration. We went through the whole topic and all the different things that can come up. Hopefully you found that useful. Take care, stay safe, and goodbye.